All right, so now that we've gotten a little bit better at solving trig equations, let's talk a little bit now about when to use a trig identity and when not to. Um, honestly, if you're looking for a rule of when should I absolutely use an identity and when should I not, I can't give you one. So this is why we practice. And you start to see situations where it's probably a good idea to use a trig identity and sometimes when it's not. So let's solve this first one. We're looking just for the answers between 0 and 2 pi. Sine squared x plus cosine x equals 1. And I guess the question I would say then is ask myself is, well, I can't do anything with this. I can't factor it because these are two different trig functions. And generally speaking, you don't want two different trig functions in the same trig equation. You want to get it in terms of just a single trig function. So I don't have any identities for just cosine of x, but I do have one for sine squared x. We know that that could be replaced with 1 minus cosine squared x from the Pythagorean identity. And so that would be good because then I'm changing this whole equation just in terms of cosine. Now that I've replaced it, we can see that the ones will actually subtract out. So now I just have negative cosine squared x plus cosine x equals 0. And here I could just factor out a cosine. You can take out a negative cosine if you want. I'm just going to take out positive cosine of x. And that'll leave me with negative cosine of x plus 1. So we have this times this equals 0. That means either cosine of x is equal to 0, or if I set this equal to 0 and solve for cosine, looks like I'm going to get cosine of x equals 1. And hopefully you've been practicing answering these. When you get this far, you should know how to find the angles that make that true. The way I teach it, remember, is I think about the trig graphs. You can use the unit circle if you want to. But I can answer both of these questions by just thinking about the graph of cosine, which I know looks like this. One period of it between 0 and 2 pi has a max of 1, a min of negative 1. And so where does cosine of x equal 0? Between 0 and 2 pi, there and there. So remember, this would be pi. So this should be pi over 2 and 3 pi over 2. So that answers this part. And where does cosine of x equal 1? It equals 1 right at 0. And the other place it does hit is at 2 pi, of course. And if you write that down, I'm not going to mark you down personally, but usually the directions, you notice they don't include the 2 pi. And I think the reason, if you go back to the circle, on a circle, 0 and 2 pi put you in the same spot. So they just, most of the time they say, well, let's not worry about 2 pi because it's in the same position as 0. So technically we wouldn't include that with these directions. Okay, so notice here, this time an identity was useful. It would help me get the equation in terms of just one trig function. Now the next one is sine squared x equals 1/2. Could I use an identity? Could I replace sine squared x with 1 minus cosine squared x? Absolutely. But why? There's no reason to. I'm not accomplishing anything. I could definitely solve it that way, but there's no reason to. To solve sine squared of x equals 1/2, I want to get sine by itself. So I want to take the square root of both sides, remembering that when I solve an equation by taking the square root, I have to remember to do plus or minus. So I get sine of x is equal to plus or minus the square root of 1/2, which if you don't recognize that, remember that that's the same as, you can split up square roots. So you could write that as root 1 over root 2. And of course, root 1 is just 1. So this is the same as plus or minus 1 over root 2, which if you're using the triangles as I've taught, this should be fine. if you're a unit circle person, remember that 1 over root 2, if you were to rationalize it by multiplying top and bottom by root 2, is the same as root 2 over 2, plus or minus. According to All Students Take Calculus, cosine could be positive in the first and second quadrants, and it could be negative in the third and the fourth quadrants. So we are going to get 4 answers, 1 in each quadrant. So we'll just go in order. In quadrant 1, you have a triangle here. This is my angle x, and we know sine is opposite over hypotenuse, 1 over root 2. And if you know your special triangles, you know this other side 1 is 1, and more importantly, you know that this angle is pi over 4. In quadrant 2, you've got a triangle that going to have the same reference angle. So this angle is pi over 4. We still have 1 opposite over hypotenuse. But the angle this time, of course, is from here to here. This is the angle we want. So recall how we do this. If you want to find this angle, go all the way around to here. Half a circle is pi. And we're going to think of pi as 4 pi over 4 in this case, because to get to the angle, we're going to want to subtract pi over 4, right? I'm going to go backwards. So this angle is 4 pi over 4 minus pi over 4, which is 3 pi over 4. Hopefully you're getting better at this. In the third quadrant, same triangle. I'm not even going to label the sides anymore. The reference angle is pi over 4. The angle I want, though, needs to go all the way around to here, which again is 4 pi over 4. But then I want to keep going, meaning I want to add pi over 4. 4 pi over 4 plus 1 pi over 4 is 5 pi over 4. And then in the fourth quadrant, and you're probably noticing depending on what quadrant you're in, you're always kind of doing the same thing to get to the angle. In the fourth quadrant, what you'd want to do is go all the way around the circle, which is 2 pi, also known as 8 pi over 4, and then subtract, go backwards until you get even with the hypotenuse. 8 pi over 4 minus 1 pi over 4 is 7 pi over 4. So there's our 4 answers. All right. So next one is just simply sine of x equals cosine of x. I said earlier that generally speaking, it's not good to have a trig equation with 2 different trig functions. But my issue now is I don't have any identities for just sine of x or just cosine of x, right? If they were squared, I could do something with it. So the way to deal with this, if you've got just a sine and just a cosine, think about what other trig function is made up of sine and cosine. And that would be tangent of x, right? Tangent of x is sine over cosine. So a sneaky way to solve this one, if I just have a sine and a cosine, is if I divide both sides by cosine of x, sine over cosine, this becomes tangent of x, and cosine divided by itself is 1. And according to All Students Take Calculus, tangent could be positive 1 in the first or the third quadrant. So, and we were just talking about this triangle. If tangent is 1, let's think of 1 as 1 over 1, right? So that I can say the tangent of x is opposite over adjacent. This is 1, this is 1. And hopefully you recognize or use the Pythagorean theorem that that's going to be root 2. And we're talking about the same triangle as the previous problem. This angle would be pi over 4. And then the other one's going to be in the third quadrant. same reference angle, pi over 4. We just did this on the previous page. You're going to go 4 pi over 4 plus another pi over 4 will give us 5 pi over 4. Now, that's a nice trick, right? If you just have a sine and cosine, you can create a tangent. But what you can't do here, so my next problem is just a small change. Sine of 2x equals cosine of x. And what is not true, if you tried to divide by cosine, sine of 2x divided by cosine of x is not like tangent of 2 or something like that. You can't, it's nothing, okay? You can't do that. This is a different angle than this one. And that's generally, if you see a problem where one's a 2x and one's an x, or one's a 3x and this one's an x, you got to do something, right? They have to have the same angle for us to solve it. So this would be a good time to use a trig identity. And recall the trig identity, the double angle identity for sine of 2x is 2 sine of x times cosine of x. Remember, in my class, other than the Pythagorean identity, I will provide these identities. I don't want you to have to memorize these, but this is the double angle identity. So I'm going to replace that with 2 sine x cosine x equals cosine x. So now at least I've succeeded in getting just the angle to be x and not 2x. But now I still have two trig functions, sine and cosine. And I said that generally speaking, that's not a good thing. But sometimes you can still get away with it. If I take this cosine and move it over to the other side, I'm going to make a comment after we finish this problem about this step that I just did there. Notice I can factor out a cosine x. And that'll leave me with 2 sine of x minus 1. And by the zero product property, if this times this equals 0, it means either cosine of x is equal to 0, or if I solve for sine x here, sine x is equal to 1/2. We just figured out where cosine of x is equal to 0, so I'm not going to rewrite it. Remember, on the first problem, we drew the graph and we found that cosine was equal to 0 at pi over 2 and 3 pi over 2. Sine of x equals positive 1/2. All students take calculus in either the first or the second quadrant. In the first quadrant, this is my angle. Sine is opposite over hypotenuse, opposite over hypotenuse. And you should know this triangle, this is your other triangle. If this is 1, this is 2, this side is √3. And more importantly, the angle opposite this one is pi over 6. And that's my angle for the first quadrant. And then for the second quadrant, same triangle. So this angle is going to be pi over 6, but it's this angle I want. So to find it, we'll go all the way around. This time I know that's pi, but I want to think of it in sixths. I want to think of this as 6 pi over 6, and then subtract pi over 6 so that I'm even with the hypotenuse. So that gives me 5 pi over 6. So I have actually 4 answers here. Okay, a couple more. Oh, I said I was going to make a comment. Let me go back to this one here. Okay, watch out on this one. I'm going to highlight this step here. I said warning, maybe watch out. What you don't want to do here, it's very tempting to do this when we're at this step, is to say, oh, why don't I just divide both sides by cosine? And therefore they cancel, and I end up with 2 sine of x equals 1, or sine of x is equal to 1/2. that was part of our solution, right? We did want to find places where sine of x is equal to 1/2. But you see, if you do this, you're going to miss out on the other two solutions, aren't you? By dividing out the cosine, you miss the fact that we should also be looking for places where cosine is equal to 0. So generally speaking, it's dangerous to divide out trig functions or even x's, right? If you're doing algebra, you're always better off factoring, moving things over and factoring. So you don't want to do this. Okay. Okay. So this, two more examples here. All right, here's another sine of 2x. Like I had on the previous problem, we used an identity for that one. But think about what would happen if I tried to use the identity here. I'll go over here. If I tried to use the identity here, the identity for sine of 2x is 2 sine x cosine x equals 1/2. What am I going to do here, right? This isn't useful unless, this was equal to 0 or something, right? If it's equal to 1/2, I'm kind of stuck, right? There's not really much we can do. So in this situation, I wouldn't want to use the identity. So that's what I'm talking about. You have to do a lot of problems to kind of get some, and sometimes you try it. If you use the identity, realize you get stuck, then you go back and look at it differently. What's different here, the previous problem was I had sine of 2x equal to trig function. And so that helped me out by using the identity. But if I've just got one sine equals a number, then we're going to use the other technique that we talked about previously, which is to first just pretend that that's just x. If you were trying to find where sine is equal to 1/2, we just did that on the previous problem. That can happen in the first or the second quadrant. And you'll recall from the previous example, okay, just to save time, sine of x equals 1/2 at pi over 6 and 5 pi over 6. So we would have that answer in the first quadrant, 5 pi over 6 in the second quadrant. And then this is, remember, I call this the cover-up method. If this was just sine of x equals 1/2, these would be my two answers. But instead of x equaling these two answers, it should be 2x that equals those two answers, right? And if this was 3x, you would say 3x equals those answers, whatever's inside there. But it is x that we want. So if 2x equals pi over 6 and 5 pi over 6, to get x by itself, what I want to do is divide by 2, which is the same as multiplying by 1/2. So that gives me pi over 12 and 5 pi over 12. Now, we talked about this on a previous video. If we want all the answers between 0 and 2 pi, there's going to be more answers here, and we find those by adding the period. The period for sine of 2x, right? If I was graphing y equals sine of 2x, we know that that 2 is going to cause a horizontal compression, which is going to shrink our period by half. So the normal period of sine is 2 pi. It's going to cut it in half. So the period is going to be pi. So what we want to do to these two answers is add the period pi. But if I'm about to add pi to pi over 12, we want to think of pi as 12 pi over 12. Plus pi over 12 gives me my next answer of 13 pi over 12. And then if I do the same thing here, I'm going to get 17 pi over 12. Now, reminder, how do you know when to stop? If I kept going, if I added 12 pi over 12 to this answer, that's going to give me 25 pi over 12. But notice that's over 2 pi. 2 pi and 12ths would have been 24 pi over 12. So we know we've gone too far. This is over 2 pi. So we can just stop with these four answers. And then last one here. Now I have sine of 2x equals cosine of 2x. And we have identities, right? We have double angle identities. But now think about this. If you tried to do the identities, put identity, the only identity for sine of 2x is 2 sine x cosine x. You can actually get like 3 identities for cosine of 2x, but the most important one, the one I focus on in this class, is cosine of 2x is cosine squared x minus sine squared x. Well, look at this. That doesn't look any better, huh? I mean, and I've got 2 cosines, 2 sines. I could convert it, this to a sine if I wanted to, but then I still have a cosine there. I'm not going to say it's impossible to go from here and get the answer, but it certainly seems like it would be difficult. So instead, notice that this goes back to a previous problem. What is nice about this is I have 1 sine and 1 cosine, and they both have 2x. So that suggests I can do the trick I did earlier, which is to divide both sides by cosine of 2x. Because it does work with the division, sine of 2x over cosine of 2x, as long as these angles are the same, that equals the tangent of 2x. And of course, this is equal to 1. Now, where does the tangent function equal 1? We did that on a previous problem. I'm going to shorten this up again. On number 3, we found out that the tangent function equals 1 at pi over 4 and 5 pi over 4. So that would be in the first quadrant or the third quadrant. Pi over 4, 5 pi over 4. Same idea as the previous problem. If this was just x, tangent of x equals 1, then x would have been pi over 4 and 5 pi over 4. But since it was tangent of 2x equals 1, that means that 2x equals these angles. And to get x by itself, I'm going to multiply by 1/2. That's going to give me pi over 8 and 5 pi over 8. And just like the last problem, there's going to be more answers, which I want to find by adding the period. Okay. Now, if I add the period, whoops, sorry. What we have to remember is the period of regular tangent. Okay, let's quick review here. Remember, the graph of tangent has 2 vertical asymptotes. Looks like this, and those asymptotes are at negative pi over 2 and positive pi over 2. And if you go past this, the graph of tangent's just going to repeat itself. It's just going to do the same thing. So the period, as we've discussed earlier, is the distance between these 2 asymptotes, which is pi. The normal period of tangent is pi. But since we're dealing with a tangent of 2x, just like the previous problem, that is going to compress our graph by a factor of 2. So the period of our graph is going to be, I'm going to say, for tangent of 2x, the period is going to be pi, and I divide it by 2. So that's what I'm going to be adding to each of these answers. I'm going to add pi over 2. Now, if I'm going to add pi over 2 to pi over 8, I want to think of pi over 2 as 4 pi over 8. And this is just a weird thing with tangent. Notice when I add 4 pi over 8 plus pi over 8, I actually get 5 pi over 8. That's actually why I knew that was going to happen. That's why I drew the arrow here. But okay, so you end up getting the second answer, which we already have. So what we do, let's just keep going from here. If I add 4 pi over 8 to that, I get 9 pi over 8. If I add it again, I get 13 pi over 8. And if I added it one more time, I would end up with 17 pi over 8. In eighths, 2 pi is 16 pi over 8, so I can tell that I've gone too far. That's greater than 2 pi. So these would be my 4 answers. All right, so hopefully, I know we've only done 6 examples, but hopefully that gives you some insight into how to know when to use an identity and when not to use an identity. Keep practicing. That's the only way you'll get better.